Bridge selection is a complicated process as many parameters need to be evaluated. Information such as span length, site geology and foundation requirements, design loads, surrounding geographical features, width requirement, clearance requirement below the bridges, transportation of construction materials, erection procedures, and construction cost and duration etc. generally need to be considered during a bridge selection process. Within all the bridge selection considerations, the two primary factors are estimated cost and constructability. As a major consideration for selecting different types of bridges, a desirable project design must meet budget requirements and also has low operation and maintenance costs. The task of construction requires an optimum amount of work and a minimum length of infrastructure closures during construction. Aesthetics consideration, on the other hand, is to have a design compatible with the surrounding community and sometimes to provide an attractive gateway. Other evaluation criteria are safety and environmental impact. Depending on the required span, a number of different options should be considered. For example, if the span falls into a range of 400 to 1600 feet, it is very likely that an Extradosed bridge will be one of the bridge types to be considered. Depending on the span, a preliminary screening process can generally remove some bridge types from further consideration. However, the final decision among different alternatives of bridges normally requires a comprehensive analysis. Cost is generally one of the other major considerations. For example, information collected from one of the telephone interviews indicated that during the bridge type selection process of the Golden Ear Bridge, the contractor considered various options such as box girder, truss, cable stayed, and Extradosed. Eventually an Extradosed bridge design was selected through a comprehensive cost comparison. The evaluation indicated that if the span is right, such as in the case of the Golden Ear Bridge, an Extradosed bridge can be competitive in the cost-based analysis. The methods for cost-effectiveness analyses including life cycle cost analysis (LCCA), value engineering (VE), and criteria-based bridge selection procedures that can be used for general bridge selection are summarized below. Life cycle cost analysis (LCCA) is shown in Chapter 4. An Extradosed bridge will probably initially cost more than a conventional girder bridge, yet would cost less than a cable-stayed bridge of the same length. However, an Extradosed bridge is also expected to be less expensive to maintain over a longer-term basis, compared to a cable-stayed bridge. Therefore, it is important to examine the overall cost-effectiveness of Extradosed bridges over other types of bridges. LCCA is a process for evaluating the total economic cost of an asset by analyzing initial costs and discounted future expenditures, such as operation, maintenance, and repair (OMR) costs, and user and social costs over the service life of the asset. While a bridge with a longer service life is generally preferable, the maintenance fee increases along with the time or use of a bridge. The LCCA methodology has some important characteristics that allow composites to be evaluated on an equal basis with existing construction materials. The method is project-based, which means that materials are compared based on costs to build typical structures, instead of measures such as dollars per pound of material. Value engineering (VE) analysis or multi-attribute ranking method is another tool that is commonly used in alternative selection, which covers a broader area compared to an LCCA Wilson 2005. The analysis identifies the necessary functions of a product or service, establishes a monetary value or worth for that function, generates alternatives through the use of creative thinking, provides the necessary function reliably, at the lowest life cycle cost consistent with performance, maintainability, safety, and aesthetics. VE may be viewed as a multi-peer review of project recommendations, and it is designed to gather expertise and experiences of individuals in order to produce the most effective solution for transportation needs. Since there are different concerns caused by differing preferences, experiences, and background, A support system is generally required to enable each stakeholder to evaluate and rank solution alternatives before engaging in negotiation with the other stakeholders. A VE therefore was used for bridge management decision through balanced consideration of multiple and conflicting criteria involving different decision makers, such as estate managers, project managers, and engineers. A similar approach called criteria-based bridge selection is also used for bridge maintenance or bridge-type decisions. Alternatives are then to be developed based on public inputs, together with engineering, context, constructability assessments, and budgets. In order to select the appropriate bridge type, the public can also be polled on the degree of importance that should be given over different categories such as aesthetics, construction costs, maintenance, and construction impacts. In order to find the best situation to adopt an Extradosed bridge design, it is important to understand the advantages and disadvantages of this type of bridge. Compared to conventional girder bridges, while longer spans of Extradosed bridges provide better navigation/vehicular clearance below bridges through a wider navigation channel, longer spans also lessen impact to the environment. The girder thickness of an Extradosed bridge is normally lower than that of a traditional girder bridge, thus reducing negative visual impact from the superstructure. In addition, the thinner superstructure will result in reduced self-weight of structures, which will lessen foundation costs as well as seismic loads on the substructure and foundation. Because of lower main towers in Extradosed bridges comparing to cable-stayed bridges, vertical loads are partially resisted by the main girders. Therefore, stress variations in stay cables in Extradosed bridges produced by live loads are smaller than those in cable-stayed bridges. While towers in Extradosed bridges are generally lower than those in cable-stayed bridges, less efforts and costs in construction and future maintenance is expected. In addition, the stay cables in Extradosed bridges need no tension adjustment as would be required for a conventional cable-stayed bridge, which could result in further reduction of future maintenance costs for Extradosed bridges.
One major reason that Extradosed bridge construction methods have not come into widespread use is the lack of specific design standards as in some countries. As mentioned in Chapter 2, with the exception of Japan, there is no widely accepted design rule and/or code that provide design standards for Extradosed bridges. The reference is available only in Japanese language. On the other hand, given the Extradosed bridge's intermediate design, it is often considered as relatively expensive compared to girder bridges and material inefficient compared to cable-stayed bridges. In many cases, the spans of Extradosed bridges are short enough that the use of cables is more for aesthetic purposes rather than as an engineering necessitated choice. However, this does not necessarily mean it is a bad choice. The Extradosed bridge type is a very elegant form, especially when the difference in cost and efficiency is small. Major reasons in which Extradosed bridges were selected include aesthetic consideration, signature bridge, structure and construction consideration, proper span lengths, unique site conditions, and seismic consideration. Underneath navigation/vehicular/hydraulic clearance and height aviation restriction. Economic, together with compatibility and environmental considerations.
Aesthetics. According to information collected, aesthetics is often an important reason why designers and owners selected Extradosed bridges. The towers of Extradosed bridges provide architects and engineers room for creative yet more economically affordable designs compared to cable-stayed bridges. Many documents stated that one of the major reasons in selecting the Extradosed bridge over other bridge alternatives is the need for a signature/landmark bridge. Rideau Bridge Figure 47A is one typical example of a bridge with aesthetic consideration, in which case the city needed a gateway structure to reflect the cultural context of Kansai District. The new Pearl Harbor Memorial Bridge Figure 47B is another example of a signature bridge. Economic. As stated in Chapter 4, initial construction cost is one of the major considerations in bridge selection. Generally, initial and future maintenance costs of Extradosed bridges are considered to be higher than that of girder bridges and lower than that of cable-stayed bridges. Compared to the prestressed girder bridge, the Extradosed bridge design could be at an advantage in total materials costs due to the reduced quantity of concrete. In addition, considering the reduced superstructure weight and potential reduced substructure cost, overall costs of Extradosed bridges are not necessarily higher than girder bridges. According to the survey from the research team, economics is one of the major reasons that Extradosed bridges were selected over other alternatives. Height restriction. Comparing to cable-stayed bridges, Extradosed bridges have shorter towers. The tower height of an Extradosed bridge is usually around 1/8 of the main span length. In contrast, the tower height of a cable-stayed bridge is usually around 1/5 of the main span. For example, the two Extradosed bridges built in Canada, North Arm Bridge Figure 5, and Golden Ears Bridge, are adjacent to the Vancouver Airport. In order to provide a sufficient glide clearance for the airplanes, the heights of the towers are closely restricted. The height restriction therefore resulted in the selection of Extradosed bridges over traditional cable-stayed bridges. Besides aviation restriction, some other bridges also have restrictions for different considerations. One example is the second Vivekananda Bridge Figure 49, constructed in India, where the bridge towers were required to be lower than the nearby temple and comparable to adjacent structures. Compared to girder bridges, Extradosed bridges generally have shallow structures. Girder thicknesses of Extradosed bridges are usually between 1.82800 m 3.96240 m, which is approximately half of the girder thicknesses of conventional girder bridges. The shallow structure can provide better clearance for the underneath traffic, either by land or waterway. The first Extradosed bridge, the Ottawa Blue Way Bridge Figure 50, is a good example of bridges requiring navigation clearance for boat traffic underneath the bridge. An example with a vehicular clearance requirement is the Pont de Saint-Remy de Maurienne Bridge, France, 1999. The bridge was constructed above an existing roadway and a river. To avoid building piers in the road or the river, span lengths were set to be 172 feet and 159 feet, 52.42560 m 48.46320 m, respectively, due to the unique site location. With the fixed span lengths, a girder bridge design would have much deeper girders than the Extradosed bridge design, which will reduce the clearance underneath the bridge. It was also not possible to increase the elevation of the bridge or build an arch bridge to provide underneath clearance in such short spans. As a result, the Extradosed bridge was the proper design in this special case. Environmental impact over bodies of water. Depending on their locations, many bridges built recently have significant considerations on environmental impact over bodies of water. Before Alan Bridge in Taiwan, see Figure 52, was planned, a study was performed to evaluate the environmental impact of the bridge before construction began. Co. 2008. As Extradosed bridges generally have longer spans compared to girder bridges, the quantities of piers and water can be reduced, which will result in less environmental impact over bodies of water. Visual compatibility is the consideration of a bridge alternative that is compatible to adjacent structures or natural appearances, or constructed with the least visual impact or interference. The Sonneberg Bridge Figure 53, in Switzerland, is located adjacent to a ski resort. Since the beginning of the project planning stage, having a design that fits the landscape was the highest priority. The tall piers and thin girders of the Extradosed bridge design provide the least visual impact on the idyllic alpine view. Construction and structure considerations. Deep ravine. Proper span length is probably one of the most important reasons that Extradosed bridges are selected over other bridge alternatives. An example of long-span designs that were used in crossing deep valleys or rivers is the Trois Bassins Viaduct in France. As shown in Figure 54, the bridge crosses a deep ravine. In order to minimize the number of piers, a cable-stayed bridge design or an Extradosed bridge design is preferable. Between the two alternatives, the Extradosed bridge option is more competitive under similar span lengths owing to the lower construction cost, better constructability, and easier maintenance. Flood zones. Another reason that Extradosed bridges were commonly selected is that these can provide proper spans for navigation, particularly in flood zones. An example is the Liuzhou-Semenjang Bridge figure 55. As the bridge is in a flood zone, the selection of an Extradosed bridge design over a traditional girder bridge design can reduce quantities of piers in the water, which not only provides better navigation clearance, but also significantly reduces the dangers of potential impact during flood season. Horizontal curvatures of structures. Another reason associated with proper spans is related to the horizontal curvatures of structures. An example is the Poo Bridge shown in figure 56. Because of the complex geometry of horizontal curvature, the span lengths of the Poo Bridge have to be reduced to match the curvature. Alternatives such as the cable-stayed bridge design therefore have become less attractive. Bridge connects to a channel. Another example of how the Extradosed bridge turned out to be an optimum alternative is the Deba River Bridge figure 57b. As one side of the bridge connects to a channel, the bridge needs to be built in a relatively low altitude in order to meet the elevation of the channel. In addition, the underneath water traffic passing capacity also needed to be assured. The Extradosed bridge design that has shallow girders eventually turned out to be the ultimate design for this case. Lombard 2004. Construction consideration. Construction consideration is one of many other reasons that may lead to decisions of constructing Extradosed bridges. During the construction of the new Pearl Harbor Memorial Bridge figure 58, the design of an Extradosed bridge has the advantage of providing appropriate span lengths through avoiding existing bridge piers, whereas the old bridge can still be of service during the period of the new bridge construction. Soil condition. Compared to a girder bridge, the Extradosed bridge has a shallow structure that also provides lighter structure weight. In situations where the soil condition cannot support heavy structures, the Extradosed bridge design is preferred. Other seismic considerations, such as bridges constructed in earthquake zones, also require decreased superstructure weights through the reduction of girder depth. The better seismic stability was considered one of the benefits of the final designs of North Arm Bridge and Golden Ears Bridge figure 59. As a hybrid of a girder bridge and a cable-stayed bridge, the Extradosed bridge design provides another option when neither girder nor cable-stayed bridges is the ultimate choice. In general, there are two most common situations in which Extradosed bridges are better choices than either girder bridges or cable-stayed bridges. When longer spans and thinner girder depths are needed, the Extradosed type is usually surpassed by the girder bridge type. When a bridge is to be constructed in deep valleys or rivers, an Extradosed bridge is generally a better choice compared to a cable-stayed bridge because of its better constructability, which in turn leads to lower cost.